In this lesson, we're going to look at notes, limits that fail to exist. Actually, it's just a continuation of things that we've done in the past. I'm just going to add another layer to this. Let's remind ourselves, limits that fail to exist are going to occur for us in two situations. Either where we have a jump discontinuity, where the left limit does not equal the right limit. And remember, when we justify, we don't use words, the left limit does not equal right limit. We use the correct notation that represents those words. The other situation we saw in which a limit fails to exist is if we have an infinite discontinuity. That implies a vertical asymptote. And remember, the justification on why that happens is because the limit approaches either positive or negative infinity, or perhaps both infinities. All right? So the other discontinuity that we've studied where a limit does still exist is at that point discontinuity. So just kind of putting all that together in what we've seen so far. All right, so what are we going to do with limits that fail to exist with the jump and the infinite? Well, we're going to determine if the limit exists. If so, we're going to find it. And if not, we have to justify one of the two justifications. And then also we're going to sketch a graph of each function. All right, if you notice 1, 2, and 3, they're all the same function. They're 4 over x minus 3. So we'll only graph the function one time since it's going to be repeated. It's the same equation. All right, so in sketching a graph of a function, that usually implies without a calculator. And for all the graphs that we are going to be asked to sketch on these notes, we should be able to do so without a graphing calculator based on our previous knowledge. All right, so let's answer this question. What's the limit as x approaches 3 from the left of 4 over x minus 3? Well, certainly if I had a graph, it'd make it a lot easier, to interpret what the answer is. We will produce a graph in just a second, but I'm going to take a different approach because let's say that you just kind of go, man, I really don't remember what that graph looks like. Is there another way that I can find this answer without relying on a graph? And yes, there is. We can find this answer numerically. So that's what we're going to do, and then we'll verify it when we get our graph in place. All right, so what's the limit as x approaches 3 from the left, numbers that are smaller than 3, of 4 over x minus 3? First thing I do is I just think about, well, what if I did put in exactly 3? What would I end up with? Well, I'd have the 4 on top still, and I'd have a 0 in the denominator. And anytime you get a numerical answer of not 0 on top, 4 is not 0, over 0, meaning a number that's not 0, non-zero over 0, that's going to imply graphically that you have a vertical asymptote. So now we know that we have an infinite discontinuity. We know that our answer is going to be does not exist because of this undefined situation with this fraction of 4 over 0. So one could say, hey, we're done, but remember they ask us to justify our answer. Well, now that we know that this is a vertical asymptote because of this numerical value we got here, or undefined, does not exist, we can say because the limit as x approaches 3 from the left of 4 over x minus 3 is equal to, and we need to know which infinity, the positive or the negative, that this graph is approaching as the x values are approaching 3 from the left. So this is where a graph would come in handy, because right now it's like, do I guess? Do I put positive or negative? No. We can do a little more inspection. We can do a little more work and get the positive or negative infinity without relying on the graph. Well, how might we do that? Well, now, instead of plugging in 3 exactly, because we already did that up here to determine that we have a vertical asymptote and the answer is does not exist, now let's pull back and enter numbers in for this x that are close to 3, but to the left of it. Don't plug in x equals 2 because 2 is too far away from 3. You might think, well, that's pretty close, but for the purposes of what we're doing, limits, we want to get really close to x equals 3. So one of the first numbers we plug in is 2.9. So let's just think about if I had 4 and I divided it by 2.9 minus 3, that would result in 4 over a negative number, 0.1. Because I'm taking a number smaller than 3 to the left of it and subtracting 3. Well, what's 4 divided by negative 0.1? Well, if you did that on your calculator, you're going to get 4. Pardon me, I think you're going to get, well, here, let's just do it on the calculator. I actually think it's 40. So I've got the function in here. Let me go ahead and go to the home screen. I got it stored in Y1. I'm just to remind you about those calculator keystrokes that are handy. Hit alpha trace. Y1, I want to evaluate it at, instead of doing this fraction right here, I'm going to go back up to the original problem. I'm going to evaluate it at 2.9, and I'm going to get negative 40. Okay, what if I were to plug in now 2.99? So what's 4 over 2.99 minus 3? Well, that's going to be a positive number 4 divided by a negative 0.01. So you can either go back up here, edit this line, adding another 9, and you're going to get negative 400. Which is the same thing as what this would be numerically if you just did 4 divided by negative 0.01. Oops. Let me do that again. You're going to get the same thing. So it's really what you want to do. If you want to enter this into Y1 and do the evaluation with the Y1, or if you want to actually just do the fractions and just do it from the home screen. But I hope you see the trend of what's happening with these numbers as these X values are getting closer and closer to 3 from the left. I mean, think about plugging in 2.999. Well, this next answer would be negative 4,000. So it's pretty obvious, I think, I hope, that we're approaching negative infinity. So we've actually, when we look back at the question to make sure we've answered all parts, we've determined the limit. It did not exist, but we had to justify and choose the right infinity. And we did that by just kind of, plugging in some X values close to 3 to the left of it and determining that we're approaching negative infinity. Okay, so I'm going to come over here and I'm going to put the graph of the function and I'm going to verify it because it asked me to also sketch a graph. Well, when we look at this original function right here, it's actually a transformation of the parent function 1 over x. And 1 over x looks something like this, where the vertical asymptote on that parent function is at x equals 0. But when we look at this equation, the transformation is to move or shift the graph to the right 3 units. So now this vertical asymptote is actually going to fall along x equals 3. The 4 actually takes the effect of vertically stretching this graph. And when it stretches it, it's just going to move it further away from the asymptotes. So you really can't visualize that, so that's not anything that you're really going to be held accountable for. Okay, so all that matters for our question is just identifying where the asymptote is and if I'm approaching positive or negative infinity. So then over here, let's go back to the problem. If I had a graph to start with, and I know this is x equals 3, if x is approaching 3 from the left, we'll get to the left of 3, then find the graph is down here, and you start traveling downward so that those x coordinates are approaching 3. So I can see graphically that I am approaching negative infinity. So hopefully that will get you going with number 2 and number 3 and answer those, and don't forget to justify. All right, looking at number 4, we can take the same approach. Let's do this first. Instead of drawing the togetherness graph, we're going to actually plug in 0 to begin with. So what happens when x is 0? Well, we get 1 over 0. Oh, that's a vertical asymptote. We know limits don't exist at those infinite discontinuities, so put does not exist. Now, which asymptote which infinity am I approaching? Well, you may remember that this graph is that kind of togetherness graph. It looks like this. So as we approach 0 from the left and from the right, our y values are going to positive infinity. If you didn't remember what this graph looked like, then what you could do is you could plug in values close to 0 to the left of it. That would be like negative 0.1. And when you plug in negative 0.1 for x and you square it, this number down here is going to become positive, but very small. And 1 divided by a very small number is going to go to infinity. Just try and play around with it and see and investigate. Next plug in like 0.01 for the x and see what the output is. And you're going to see that these numbers get increasingly bigger and bigger and bigger, suggesting that we go to infinity. All right, so hopefully that'll help you with 5 and 6. Okay, let's look at 7. Okay, try and plug in 3 first. When you plug in 3, you're going to get 5 divided by 0. That means that this answer does not exist. What's the justification? Well, because the limit as x approaches 3 from the left, I'll get this down here, is either positive or negative infinity, because we know that we have a vertical asymptote, because 5, not 0, over 0, when 3 is plugged in, suggests on a graph that we have a vertical asymptote. All right, so you could plug in numbers close to 3, but to the left of 3. You're going to get a negative number here, but when you square it, it's made positive. It's small. I would think that this these values are approaching positive infinity based on my computations that I did in my brain here. You might remember how to graph this. Again, it's the parent function that we saw back up here, shifted right 3. So now your vertical asymptote's here, and that 5 just vertically stretches the graph, kind of makes it pull away from those asymptotes. So you can investigate, what this answer is, which infinity is, by looking at the sketch of your graph. But I wanted you to kind of see that, you don't have to rely on a graph. We've got our number sense. All right, let's look down here. I want to do at least one of these down here at the bottom. So I'm going to just do kind of a few of each in each section. Determine if the limit exists. If so, find the limit. If not, justify your answer. Notice that we're not asked to sketch a graph of each function. These, with the exception of this one right here, these are not parent functions that we're familiar with. They could be if we did long division, but that's not part of our focus in this course. So if we did long division on these two problems, we would get a reciprocal answer, and that would model the reciprocal graph, but we don't have to worry about that. So we don't have to produce a graph. So what should we do? Well, exactly what we did up here, rely on some number sense. So first thing is, on number 10, I'm going to plug in 3. Well, notice now I have to plug in 3 up here and 3 down here. When x is 3 up here, I have negative 3 plus 4, so I get 1. And when x is 3 here, I get 0. Well, I know my answer does not exist because a non-zero number divided by a zero number produces a vertical asymptote on a graph. So that's our infinite discontinuity. Only thing left for me to do is figure out, am I approaching positive or negative infinity for my justification? So we've got a because. So what do? Plug in a number that's to the right of 3, so 3.1. If I plug in 3.1 here, negative 3.1 plus 4 is a positive number. That's all I care about. If I plug in a number to the right of 3, like 3.1, and subtract 3, that's a positive number. So a positive divided by a positive is a positive. So I knew up here I had an infinite discontinuity, and my justification at that vertical asymptote would either be the positive or negative infinity. All right, let's take a look at some problems on the back. So hopefully this will be good information for you to be able to finish those other ones that we didn't on the front, and then likewise on the back. Okay, notice the directions return to what they did for the first problem. Okay, so what we can do is we can try and figure out the answers to these numerically, and then we can produce a graph for each of these 3 to verify what we thought. Okay, hopefully you remember this is a parent function. Okay, you may have named it here to there or whatever y'all call it. I don't know if that's an official name, but it's catchy. It works. All right, so, but let me try without the graph to try and analyze what this answer is. So first of all, I'm going to plug in 0 like we did on the previous problems. So I'm going to end up with 0 over 0. Okay, now notice that this is 0, not non-zero. So we cannot say that we have a vertical asymptote. As a matter of fact, when we get 0 over 0 with the limit question, that implies that we don't have an infinite discontinuity, likely. We either have a jump discontinuity, where the limit does not exist, or we have a point discontinuity, okay, where the limit could exist. So we have a little more work to do. So I'm not sure yet if I should put does not exist, because if I have a point discontinuity, then that means that implies the limit exists. So really what we need to do is we need to think about, okay, what's the left-hand limit? Figure out what that is. And then we also need to investigate what's the right-hand limit. Because if these one-sided limits are the same, then the limit exists, and that suggests we have a point discontinuity. If these one-sided limits, if these two answers are different, that means that we have a jump discontinuity. And you might already be thinking, well, I know what that graph looks like. I know it's a jump discontinuity. Well, good. I hope you are thinking that. All right, but how do we do this without a graph? Well, let's plug in a number close to 0 but to the left of it, like negative 0.1. We want to take the absolute value, negative 0.1 down here. So in the numerator, I'm going to get a positive 0.1, but in the denominator, I still have that negative 0.1. These are two opposites being divided, which means that my answer is negative 1. All right, down here, okay, let's plug in a number close to 0 to the right of it, like 0.1. So I've got 0.1, absolute value of it, over 0.1. Well, the absolute value bars aren't going to serve any purpose when we plug in a positive number. So we just end up with 0.1 divided by itself, and a number divided by itself is positive 1. So these one-sided limits are different. They're not the same. So that suggests that we're going to have a jump discontinuity. So I'm going to come up here, and I'm going to say this limit does not exist. And I'm going to just come down here and put because, and look at all this work that we already did, serves our justification purpose. You could leave it just like this, and this would be acceptable. If you want to kind of tweak this and fine-tune it, then you can actually just put the notations do not equal to each other. The left limit does not equal the right limit. Do we have to do this? No, not if your work up above supports that the one-sided limits are not equal. All right, let's go ahead and remind ourselves what the graph of that function looks like. I'm going to write it in here pretty small. But up here at a y value of 1 and down here at a y value of negative 1, we have these two horizontal pieces that look something like this. And clearly from this graph, we can see that as x approaches 0, and that implies that we have to investigate, it's on our shoulders to investigate left and right hand behavior as x approaches 0, we can see that from the left and from the right, those two y values are different. 14 and 15 are similar. It's just that we take the parent function, and for this problem, we shift the parent function left 1. And for this graph right here, we shift the parent function right 5. And just be careful, sometimes students make mistakes in the shifts and everything. For example, this graph, when I shift this graph right 5, remember your y values are still up here at 1 and down here at negative 1. And the open circles fall vertically, line up vertically above and below that x equals 5. So it looks like this answer is going to be it does not exist either, because the left limit doesn't equal the right limit as x approaches 5. Let me just caution you, because what if these problems in 13, 14, and 15 were one-sided limits? Meaning, what if 13's question was actually as x approaches 0 from the left? Well, I do have an answer, and it's negative 1, and I would be done. But that's not what the question is. The question is as x approaches 0 from both sides. Had the problem just been the question, the limit as x approaches 0 from the right, my answer would have been 1, and that would have been the answer, and then I would have just left this problem. So it's real important to pay attention to what x value you're approaching, and are you approaching it from both sides or just one side as suggested by any superscripts that might be there. All right, let's look at 16 and 17. We'll do the harder one together, 17, and I'll leave you to do 16. All right, it says use left and right hand limit notation to find the requested limits. Also sketch a graph of each function. All right, I think I'm going to sketch the graph last. So I'm going to actually use left and right hand limits to find the requested limits. So here's my piecewise function. F of x is equal to the reciprocal function as long as x values are less than 4. Or f of x or y is equal to a quadratic that opens upward, because a's value is positive, the coefficient on x squared is positive. I only want the parabola that opens up for x values greater than or equal to 4. Then the limit as x approaches 4 of the function is equal to. I don't need a graph to answer this question. I'm going to use the left and right hand limit notation to help me find out what the limit is. Well, as x approaches 4 means that it's on my shoulders to make sure that I investigate behavior from the left, and I investigate the behavior of the graph from the right of 4. All right, so the limit as x approaches 4 from the left. So which of these two pieces do I pull down here for this question? Well, 4 from the left. Left of 4 means numbers smaller than 4. Smaller than 4 means less than 4, the less than sign. So the function I pull down is 1 over x minus 4. Now I'm going to just go ahead and plug in 4 and see what happens. When I plug in 4, I'm not going to worry about numbers to the left of 4. I just want to kind of investigate what happens. If x is 4, I'm going to get 1 over 0. Well, wait a minute. That's a vertical asymptote at x equals 4. That means this limit does not exist. Why? Because if I'm asked to justify, it's because, I think I'll put it over here. This left-sided limit of 1 over x minus 4 approaches either the positive or the negative infinity. Well, again, which one? Well, choose a number to the left of 4, like 3.9. When you subtract 4, you get a negative denominator, but with a positive numerator divided by a negative denominator, my graph's actually going to be approaching negative infinity. All right, well, let's go ahead and just finish this right-hand limit right here. So the limit as x approaches 4 from the right. Numbers to the right of 4 are greater than 4, so I look for the greater than symbol. So I know this quadratic equation belongs here after this limit statement. Let's just plug in 4. So 16 minus 8 is 8, plus 5 looks like to be 13. So this limit, the right-hand limit exists, and it's 13. The left-hand limit doesn't exist because I have a vertical asymptote, and that's because my y values are getting closer to negative infinity. So now how do I take all this information and come up here and respond to the limit as x approaches 4? Well, that answer has to be does not exist. These two numbers are not the same, and as a matter of fact, that's not even a number, it's an infinity. So we just say does not exist, and all your work right here will support why you have a DNE here. Let's see if we can get a graph to kind of see what's going on here. If I'm graphing this piecewise function, I really want to focus on my restrictions on x. I have a break on my graph at x equals 4, so I'm going to put 4 here. I do know that when x is 4, I have a vertical asymptote. I do know that this graph is the reciprocal graph shifted right 4 with a branch up here and a branch down here. I don't want both branches. I only want the branch where x is less than 4, so all I want is this graph, this part of the graph right here, this branch. So that tells me that as x is greater than or equal to 4, I have a parabola that opens up. Well, what does that look like? Well, I don't want to pick up a calculator, so for me, I'm just going to plug 4 in, which I already did, and I got 13. And I'm going to say maybe this is 13. I'm actually going to put this point on the vertical asymptote. I know that's weird, but it's okay. And then off of that point, I know that this parabola is probably going to open up. I think the parabola looks something like this, but all I care about is the right part of that parabola after x is 4. So now let's look at our two limits and make sure that we can justify what we got here based on our graph. What's the limit as x approaches 4 from the left? Well, here's 4, here's to the left. I'm approaching negative infinity. Yep, I got it. That limit does not exist. So, and let's look at the right-hand limit. As I approach 4, here's 4 to the right of 4. That means I'm on the graph up here, but as I get closer to x values of 4, I am going into a height of 13. I know the justification is real weird because we weren't kind of used to seeing that. We're used to seeing a complete vertical asymptote, or a jump discontinuity, but there are sometimes these weird graphs. And your DNE is, again, like I said, justified in how you've expressed your one-sided limits down here. All right, so try this one on your own. This one's not as weird as this one. This is pretty straightforward, but you do have to know how to graph this type of piecewise function, which is pretty basic, without a calculator. But if you get stuck, go ahead and pick up your calculator to inform what you think you should be putting down there on paper. All right, we have one more section, so we'll do one problem down here. Let's see if I can figure out which one's the most difficult one. I always like to do the most challenging one. I don't know, I guess 20. It says, find constants, A and or B, find the numbers, that's what constant means. Let's find the numbers for A and B such that the limit exists, remember what that means, left limit equals right limit, at the indicated x values. Okay, so at x equals 1, that's where our break is occurring, at x equals 1. We want the limits to exist. We want to have a point discontinuity there, or we just simply want the graph to be continuous through x equals 1. All right, so we've got to find values for A and B so that the left limit equals the right limit at x equals 1. All right, so the limit as x approaches 1 from the left. Numbers that are smaller than 1 are to the left of 1. Numbers that are less than 1, so I'm coming up here and I'm looking for the less than symbol. So this one-sided limit right here has to be connected to the square root of 1 minus x. It would be wrong to put x minus b down here when we're talking about numbers to the left of 1 or less than 1. Let's just straight up plug 1 in and see if we get an answer. Well, you do. You're going to get the square root of 0 or 0. Okay, so now down here in the bottom equation, let's do the right-hand limit. I'm looking for A and B. Where'd they go? The limit as x approaches 1 from the right. Numbers that are greater than 1, that would be x minus b. Let's plug in 1 for the x, and we're going to get 1 minus b. Well, remember, if we want the limit to exist, then we have to take the one-sided limits and set them equal to each other. So what's 1 minus b equals 0? Well, I'm going to add a b to the other side, make it positive. That's how I'll take care of that. 1 is equal to b, so that's my answer, b equals 1. I had no a to find, so I'm good to go. That's the only thing I had to find. I don't see a problem where we're missing both A and B. It looks like we're just missing either A or B, so hopefully it won't be too bad. So I'll let you just handle the rest of them from there.